Okay, now we're going to take everything you've learned and combine it in looking at the atmospheric circulation. The atmosphere has a lot of components, and all you've been working your way through various ones each week. Now we're going to put them all together to see what happens, what kind of planetary scale atmospheric circulations exist, and what their impact is on the actual weather you experience or on climate itself. So if you had a nice non-rotating Earth, we don't, uh, you would have one big circulation on the northern hemisphere where it was dark. On one side, you would have cold air sinking, so that would be the coldest spot. On the other side, you'd have warm air rising, so you just have this continuous, two big convective cells form. However, we don't have that. We have a rotating Earth. So that causes our patterns to split. So think about this. It causes there to be low pressure along the equator, convergence, high pressure about 30 degrees north, low pressure around 60 degrees, and more typical high pressure at the lower levels over the poles. So they're your belts of wind. So if you have that, what I would expect then, if I'm looking at a weather map, is I see a lot of high pressures right around 30 degrees north, lots of lows up towards 60 degrees north. And remember, these move up and down depending on the season. So with that, let's just take a quick peek at that as well right now. And here should be coming up a weather map. 60 degrees north is up about here, say. So one low, another low, another low. Looks to me like that looks pretty reasonable. A lot of lows moving across right around that latitude. So if you were in the wintertime, that latitude might drop down to 50 degrees, so maybe more of the lows would be coming through here. But it's still the same thing, and maybe in the winter it might move it up a little bit further north. Oh yeah, what about the high pressures? Well, if I'm going to look at them, 30 degrees is right off the southeast coast. We get a Bermuda high, and there's another high sitting out here off the Pacific Ocean in the same general area. So today's weather map actually looks like you would expect on a global weather pattern. So all that we've learned about, now we can apply in what we're looking at. So we have high pressure, like it says, 30 degrees, a low pressure further up. And these are semi-permanent. If you were to average out over the course of the year, these would be, January would be where you expect to find the big high across most of the Atlantic. Low pressure is up fairly far north. High pressure over Siberia. However, notice a couple things. In the summertime, it switches. Now all of a sudden you have low pressure over areas like the Mid-East and all. And that changes dramatically what the weather is going to be and how the weather is going to populate. But we've talked about the subtropical anticyclones. Polewards, you have the fronts that come between the two, all the Aleutian lows. And you have that big polar vortex sitting up on the very top of the world. Just sits there, circulates around. If it's very strong and very intense, you have very, very cold air in it. So remember, pressure is going to drop very fast from the surface. And you wind up with an intense low pressure system aloft. Other times in the mid-latitudes, we have more of a wavy pattern, west to east flow in the northern hemisphere. The opposite direction in the southern hemisphere. And the tropopause stays pretty low in the polar tropopause, obviously with the polar vortex up there, it pulls the tropopause down, while in the tropics, the tropopause goes up. And in between, you get all these fronts, and the tropopause goes up and down, literally. In the southern hemisphere, in the tropics, you get a persistent trade wind inversion. And the intertropical convergence zone, kind of funny thing. Over the oceans, you get lots and lots of heating from the sun, but the temperature doesn't change a whole lot. Why is that? Well, you get lots of evaporation, right? Latent heat. Boy, the specific heat of water is extremely high, so it takes a tremendous amount of heating to warm the ocean, and the ocean does not warm a whole lot in the tropics. So the actual warmest temperatures on the ocean vary very little between January and July, so that intertropical convergence zone follows those warm water, so it doesn't change a whole lot. Now, over a continent, wow, what a difference. Continents don't take as much to heat up. You get much, much more sensible heating in them. So in July, the intertropical convergence zone literally goes all the way up to the northern part of India, into China, whereas in January, it's way down south. That makes for major differences in the weather in that area of the world. What it does is change completely the wind direction. So in the summertime, you get a very wet monsoon system coming in, and it persists. Once that intertropical convergence zone moves north of it, it's not moving a whole lot during the summer. So for months on end, you get these winds coming in off the water, causing tremendous rain. Wintertime, it moves south. You get the winds off the continent, very dry. So they have very pronounced wet and dry seasons in that part of the world. Oh yeah, with these high pressure systems and the trade winds. Think about it. If you're on the east side, like San Diego is, the air is going to be coming out of the north. So it's cooler air. It's going to tend to sink around the high. So you wind up not getting too much in the way of moisture coming in, even though it's coming around the ocean. So you wind up with a very dry season, particularly in the summertime. However, Charleston, South Carolina, on the other hand, pulling up a lot of warm, humid tropical air and pulling in a warm Gulf Stream, because the atmospheric circulations tend to influence the ocean circulations. So you wind up with a lot of moisture down there. And here is the ocean circulation. Look at it. You have a big North Pacific gyre and North Atlantic gyre. And that North Atlantic gyre rotates clockwise. So that is why on the east coast of the U.S., we get warm Gulf Stream currents. It keeps us warmer in the wintertime, literally, than we would be otherwise. And if you're over in the Canary Islands, you have a north flow bringing in cooler water, Spain, off the coast of Spain. That's why they tend to they don't get as much in the way of hurricane weather later, and they also tend to have a drier climate. So you can see the North Pacific gyre as well. We actually have a monsoon in the North America too, called the North American monsoon. It occurs in the southwestern U.S. In the summertime, you get intense heating. Remember, the sun's further north, and there's a high plateau in Mexico, northwestern Mexico, that heats up tremendously. What's it do when it heats? It causes low pressure at the surface and high pressure aloft. So what it triggers is that low pressure at the surface pulls moisture in, both from the Pacific and from the Gulf of Mexico, pulls it northward, and the high sits over top of it. You wind up with a lot of thunderstorms developing in that area. Once that sets in, it can last for a month or 2 months. Okay, Rossby waves are long waves in the atmosphere. So again, let's take a peek at something here. So let's take a look at long waves in the atmosphere here. This is a morning analysis, confusing. Has winds, contours, and it's roughly at 300 millibars. So low pressure, which you would expect over the poles, wavy pattern, very wavy pattern. Wave here, wave here, wave here, here. Not much over the Atlantic right now. Another one over Greenland, maybe towards coming into there. Several on the other side of the world. Okay, when you're looking for Rossby waves, you're trying to look for something that literally extends well south and is pretty big, broad. I would argue there's a Rossby wave here. Maybe another one might be right in here, which is kind of close together, unusual. Probably one trying to develop along the East Coast. And another one on this side of the world. So there's probably about 4 to 5 Rossby waves right now. So they're long waves. And when they're in there, little waves come in, deepen in those long waves where they are, and make more storms. So when you get a Rossby wave, you kind of look where, and it doesn't move as frequently as these little lows like this will move around the globe. They tend to be where storms that form one after the other, and you wind up getting a lot of bad weather. And we've had one in the Midwest, because look at all the severe weather and the storms that have been moving up through the Midwest. And this Rossby wave has been there for a while. It's beginning to move to the east now, changing things up a little bit here. So that's your Rossby waves. So zonal flow is when the flow's very uniform, moving basically from west to east. There's little ripples in it. You can get little weak low pressure systems, but you tend to not very much. You don't get really strong high pressure systems. And the temperatures actually work out to be pretty close to normal. Now when you get meridional flow, then you get these very deep troughs, much more intense, and you wind up with more of a contrast in air masses, so you can have more intense low pressure systems and high pressure systems. Sometimes there's blocking that goes on, and in the springtime especially, there's a lot of blocking that sets up. Think about a block. What you're doing is basically pulling down a chunk of air from the Arctic or whatever, and that just sits there. It can't move east or west. You see, it doesn't have any good flow coming into the western part. Kind of like when you're seeing these pools or ponds, when you're flowing along and all of a sudden you get an area where maybe something just disturbed the current and it just keeps circulating. A piece of wood just circulates and circulates right there. That's what happens in the atmosphere. These blocking patterns can persist for months, so literally weeks at a time. And when it does, it causes either a lot of drought or a lot of rain. Here, for example, was one that occurred in 1993. It just set up over the Midwest, and it produced tremendous rainfall in the Midwestern part of the U.S., while southeastern U.S. had nothing. It was simpler again. One of the other things is there's a polar front that develops. Remember, to the north, it's going to be lower pressures aloft, higher pressures to the south. So what happens if you look horizontally, you get a pressure gradient, like we've talked about. And the more intense that gradient is, the stronger the winds are going to be, and the bigger the jet stream is going to be. And now, remember, the northern hemisphere is most intense, the coldest. The further up in the atmosphere you go above these low pressure systems. So, and the Coriolis effect to balance that, you get jet streams. Where the polar front is well defined, the jet streams are going to be the strongest. You get a seasonal shift. Sometimes summertime, the jet stream will go further north. Wintertime, it might go actually pretty far south. And there may be more than one jet stream at a time. So, since we're talking about jet streams, I'll show you one right now that is occurring. And here's your jet stream. We have a jet stream coming in off the Aleutians into the western, just north of the western part of the U.S. It's another jet right here coming in across the northern part of the United States, across northern Ohio there. And here's another little jet actually coming in off the Pacific, called a subtropical jet. It does occur in the wintertime. You wind up getting an extra one of these sometimes. And this can aid in the amount of precipitation and all that comes into the United States. And here you have another jet coming across the Atlantic. So you can see different jets, all kind of very intense winds. And we're going to talk about where the winds can be, cause divergence. The left-hand front quadrant of a jet, the front being where it begins, is called divergence, and the right rear and trigger divergence. So those are the two areas we look for storm development, low pressure systems to form. So let's go back here again now, moving along a little bit. You can see these short waves rippling through the flow. We just talked about where these divergence things are. And they form where you have your divergence aloft, you get the air rising, you get the low pressure. Where you have convergence aloft, you get sinking, and you get high pressures. And there's that jet, and I was talking about the divergence left front and right rear, convergence left rear, right front. If you're looking for high pressure, you're looking in this area or this area. Looking for low pressures, you're looking in these areas. El Nino, it's literally an ocean and atmospheric circulation. Right now we're in La Nina, which means the Pacific Ocean is actually colder than normal in a certain area of the Pacific. La Nina tends to cause exceptionally strong trade winds atop the tropical Pacific, where El Nino causes the trade winds to weaken there. But one of the interesting things is about El Nino, though, it causes the winds to increase aloft over the Atlantic Ocean and affects hurricanes that way. Now, La Nina, on the other hand, actually is an enhancer of hurricanes. And here you can see the temperatures up and down all over the place. But right now we're in a cold period. Another thing that occurs along the coastline of water is the Ekman spiral. Basically, let's take Nags Head, North Carolina. The beach there faces to the east. If you have the flow of water coming up from the south there, if you have a southerly wind on that, you're causing a Coriolis effect to begin to impact the ocean current because it's moving northward. So it begins to turn to the right with that Coriolis impact. And when it deflects to the right, what it does, it pulls away from the coast. And as it begins to turn more and more to the right, it actually goes deeper and deeper in the ocean. And you begin to push up the cold water underneath, nutrient-rich water along the coast. For example, Nags Head many times in the summer will have an 80-degree temperature on the surface one day, and the next day it'll be in the 50s. And you walk out, you think you're going to have a great swim, and wow, what a difference in the water. And this is all due to the Ekman spiral. Also occurs along the equator. El Niños, we've talked about them and their impacts. Warm phase, cold phase, La Nina. Knowing about them can impact, for example, how much rain you might expect to get in California in the winter. Maybe it impacts how they distribute the water that year. Maybe it changes the fishing habits in the Pacific, so they'll know how to fish. There are other major circulations. There's North Atlantic oscillation. This seesaw variation in air pressure is between the subtropical high down over the 30 degrees and the subpolar low. It has a major impact on the eastern U.S. as far as wintertime weather. And if you can forecast it well out in advance, you can actually predict what the winter is going to be. But we've never been able to do that very well. But when it's positive, you get stronger winds sometimes, blowing across North America, cold air masses across the eastern and continental U.S. But negative impacts might be wild, but you can also get some major snowfalls on the east coast of the U.S. with negative impacts. And you can see here what's going on with the North Atlantic oscillation. And it varies literally over about a 2 to 3 week cycle. That Arctic oscillation this past year, when it's extremely strong, Arctic oscillation occurs, you wind up literally messing with the polar vortex. And when that happens, you wind up allowing more cold air to come out of the Arctic and into Canada and possibly into the U.S. And that's what happened this year with Texas getting into it and all. There's one from the Arctic oscillation. And you can see that here. When it's weaker, negative phase, more and more cold air comes into the U.S. Positive phase, less cold air. And there's a Pacific decadal oscillation that is out there as well, which impacts the west coast of the U.S. mainly. So we're looking at all these major circulations here. Madden-Julian oscillation is basically a group of thunderstorms that develops in the tropics and traverses the globe literally over 30 to 60 days. And there will be several of these going across the globe. And depending on the phase of them, they may interact and actually help develop extratropical storms, or they may inhibit things like hurricanes from developing, or they may enhance development of a hurricane. So this is all dealing with the global circulation. So I hope you got a little bit out of this. And just, if you have any questions, let me know.